Assalamualaikum and hello everyone. We are from Group 1. This is our project called Solar Power System. Before we begin, let me introduce my team members. Here we have Amira Aiman, Nuri Husna, Deluyanti, Matthew and myself, Ayu Masara. Now, let's start with a quick introduction. These are electric power systems that collect and concentrate sunlight to generate the high temperatures needed to produce electricity. They use solar energy collectors made up of two main components, mirror and reflector, that capture and focus sunlight onto a receiver. They also include a thermal energy storage system that collects heat during the day and store it, so that electricity can still be produced in the evening or when it's cloudy, making it more reliable than solar panels alone. Now, moving on to some challenges. First, it is hard to control the system as sunlight keeps changing throughout the day. So, we need more control to manage the heat. Second, this system takes up a lot of space, which can be a problem near cities or factories. But there are some great benefits too. They have efficient heat to electricity conversion, they store heat better than electricity, and they are much cleaner than using fossil fuels like coal and gas. As for applications, these systems are used in water heaters for homes and buildings by transferring heat to water. They are also used in industries. For example, a solar-powered coffee roaster that can roast over 100 pounds of coffee per hour using just sunlight.
This is our process flow diagram which follow Rankine cycle. The system has two turbines to produce more work and multiple pumps to maintain flow inside the system. First, we collect the source from solar collector and it goes into heat exchanger to transfer heat into Rankine cycle, which goes into turbine to produce work, and after that it goes into the condenser to condense the steam into liquid, and also into increasing the pressure by going through pump and regenerator to preheat the liquid before it enters the heat exchanger. Here there are two streams that goes through this heat exchanger. The first stream is from stream 4 to stream 5. The temperature increased from 40 degrees Celsius to 380 degrees Celsius. Meanwhile, the other stream is from stream 7 to stream 8. The temperature decreased from 400 degrees Celsius to 133.52 degrees Celsius. For stream 8, the state is saturated vapor, and for all streams, the pressure remains constant. Heat change at regenerator, we assume that it is insulated regenerator. So when pressure constant, the temperature of the outlet regenerator is equals to the highest temperature of the inlet regenerator. This is the calculation that we did from stream 1 to stream 8, which contains pressure, temperature, enthalpy, and also entropy.
For the calculations, we found the work of the turbine by adding the equation of work from turbine 2, where enthalpy 5 enters the turbine while enthalpy 6 leaves the turbine, and work from turbine 1, where enthalpy 1 enters the turbine while enthalpy 2 leaves the turbine. The values for H1, H2, H5 and H6 are obtained from the table shown previously. The total work produced by the turbine is actually negative 1422 kJ per kilogram by adding the subtraction of H5 from H6, H1 from H2, indicating that the work is done on the system. For the calculation of the pump, we found the work of each of the pumps by using the following equations. Work for pump 1 is obtained by multiplying the specific volume, which is 0.001006 meter cube per kilogram, with the subtraction of pressures 7.385 and 5.629 kilopascal, and work for pump 2 is obtained by multiplying the specific volume 0.001008 meter cube per kilogram with the subtraction of the pressure. Next, the W net is obtained by subtracting the pump work from turbine work. The mass flow rate is calculated by dividing the output power determined by the grid, which is 200 megawatt, with W net, hence obtaining the mass flow rate, which is 140.67 kg per second.
Now I would like to discuss about the energy input and the efficiency. So the energy input is the energy from the solar collector to the turbine. So the energy is Q over 2. So why is Q over 2? Because we have two streams, stream 1 and stream 5. And due to the both stream have the same output of pressure and temperature, so Q over 2 is applied to one stream for simplified calculation. So we are going to find the H4 prime first to get 167.7 kJ per kg. Then apply the energy balance equation, we will get the Q in is equals to 6136.6 kJ per kg. And for the efficiency is about the work net, which is 1421.8 kJ per kg divided by the Q in. So we will get 23.17%. And next, it will be the energy at the solar collector. So previously we found that the Q in is 6136.6 kJ per kg times by the mass flow rate. So the energy flow rate will be 863,265.522 kJ per second. By using this, we can find the mass flow rate at the solar collector. So the mass flow rate of the solar collector, by applying this equation, we will get 1567.86 kg per second. And next, it will be the heat rejection of the condenser. So the Q out is H2 minus H3. So it will be 2376.5 kJ per kg. And the Q out, by multiplying the mass flow rate, so the energy flow rate will be 334,302.255 kJ per second. That's all.
And next, for the comparison, we compare our proposed solution, which is solar power plant, with fossil fuels and solar PV power system. We compare it with 6 aspects, which is thermal efficiency, capacity, process cycle, fuel sources, alternative fuel, and environmental impact. The thermal efficiency for solar PV power system is 15.3%, while 42.8% for the fossil fuels and 21% for our solar power plant. And then the capacity for our solar power plant is 100 megawatt and 1,400 megawatt for the fossil fuels. And for the solar PV power system is 420 kilowatt. And the process cycle that used by solar PV power system is grid-connected PV solar system, and water Rankine cycle was used for fossil fuels, and our solar power plant used organic Rankine cycle. The fuel sources for the solar PV power system is sunlight, and fossil fuels use coal, and our solar power plant use Earth's internal heat, which is R134A. That was our working fleet. And then the alternative fuel for the solar PV power system is silicon, and the fossil fuels which can use biomass. And then for our solar power plant, we can use more efficient working fleet. Next, for the environmental impact, solar PV power system has zero emission during the operation, but it needs more spaces for the panels. Then for the fossil fuels, it will release greenhouse gas such as carbon dioxide, and it also can cause the water pollution. Then our solar power plant also have zero emission during the operation, but it also needs a lot of spaces for the panels.